In this ROS2 lesson, you will learn the basics of URDF modeling in ROS2. URDF is an abbreviation for Unified Robotics Description Format. This is a file format that's used to specify the geometry and model of robots in ROS2. Also, you will learn how to write launch files in ROS2 for displaying the URDF models. Besides this, you will also learn how to display the robot model in RViz. Currently, you can see a 3D model of a simple manipulator with 2 degrees of freedom. This is the main RViz window. RViz is a visualization software integrated with ROS2. Finally, you will learn how to adjust the properties of the visualized model in RViz and how to visualize coordinate systems. This lesson is developed under the assumption that you're using ROS2, Humble, Hawksbill, and Ubuntu 22.04. There will be a separate lesson explaining how to perform the same tasks in ROS2, Irwini, and Ubuntu 22.04. For those of you interested in professional ROS2 training, we are currently developing several courses on ROS2. These courses will cover both the basics and advanced concepts of ROS2 and applications. The lesson that you're currently watching is made in March 2024. In several weeks from now, the first ROS2 course module will be ready. You can access this module by visiting a link that will be provided in the description below this video. The courses will be posted on this website under this section. The modeling procedure is thoroughly explained in this lesson, and you have to carefully follow every step of this lesson in order to properly implement the model. This lesson is also accompanied by a step-by-step manual, URDF, and Python files. A link to the manual and all the files is given below this video tutorial. This lesson is developed under the assumption that you're using ROS2, Humble, Hawksbill, and Ubuntu 22.04. Consequently, the first step is to verify the Linux and ROS2 distributions. For that purpose, open a terminal, and over here I will resize this terminal window such that you can see at the same time the terminal and the manual. We can check the Linux distribution by typing this. Over here I can see that I'm having Ubuntu operating system and I can see the version 22.04. If you don't see 22.04, for example, if you see 20 point something, this means that you need to install the proper Linux distribution. That is, you need to install 22.04. This last number over here doesn't matter. Next, we need to check the ROS2 version. If you properly installed ROS2 Humble, you will be able to source your environment by executing this command. And after executing the source command, you can print this environment variable, and as the output you should see Humble. This is very important. If you don't see Humble, then stop watching this lesson and install ROS2 Humble. I created a separate video tutorial explaining how to do that. The step number 2 is to install the necessary packages and programs. I always like to start from scratch. Also, I'm requesting from you to close the original terminal, mainly because we want to teach you that every time you want to do something in ROS2, you have to source the base environment. So let's start with that practice. Every time you open a new terminal, source the ROS2 base environment by running this command. Let us now install the necessary programs and ROS2 packages. First, let us update the system and install gedit editor. Note that gedit is not a ROS2 package, it's actually an editor. To update the system, we need to execute these commands. Enter your password. And be patient. Okay, After that command, you need to run this command. And after that, you need to install gedit. As you can see over here, in my case, gedit is already installed. This is because I installed gedit before creating this video tutorial. Next, we need to install several ROS2 packages. We need these 3 packages and I will explain them later on. For the time being, let's first install them. As you can see already, over here, this package is installed. However, in your case, you will see the installation progress. Then install this package. Again, in my case, it's installed. However, in your case, you will see the installation progress and install this package. Okay, let's explain these packages. Robot State Publisher. This package takes joint angles or displacements as inputs and publishes 3D poses of the robot links using a kinematic tree of the robot. The state of the robot is published to TF2. TF2 is a transform library that's used to keep track of the relationship between coordinate frames over time. It maintains a tree structure describing the relationship between the coordinate frames. Also, this library enables us to transform vectors, points, or any quantity between any 2 coordinate frames. Then we install the package called Joint State Publisher. This package is used to publish joint states. It publishes messages of the type sensor messages joint state. Then we install the package called Joint State Publisher Graphics User Interface. This package is used to graphically set and publish joint state values for a given URDF model. We will explain this package later on in this tutorial. Next, we need RViz2. RViz2 should be installed together with ROS2. However, it's always a good idea to double check if RViz2 is properly installed. To check that, we can simply execute this command. And you can see the path to the RViz2 package. This means that we have properly installed RViz. In step number 3, we need to create the workspace and our package. Again, to practice how to source the environment, open a new terminal by clicking over here and source our base environment. Then, let's create the workspace folder. We can do that by executing this command. This command will actually create 2 folders. It will first create the folder called WS Humble URDF, and inside of that folder, it will create the source folder. Okay. To create an empty workspace, we will navigate to our workspace folder, and in that folder, we will simply type "build." Ignore this error. We currently created, or better to say initialized, an empty workspace folder. If you type LSL, you can see the structure of this folder. Let's create the package. First of all, let's navigate to the source folder. In the source folder, we will execute this command. This command will create the package called URDF Humble Test. And you can see it also over here. Okay, let's continue. The name of the package is URDF Humble Test. The package source files and folders will be actually in this folder. Let me show you that folder. It is in this folder. Over here, we will place everything. Let's again learn how to navigate to this folder by using a single command. I can type this and I will go to the same folder. Inside of that folder, we need to create 3 subfolders. The first folder is launch, the second folder is URDF, and the third folder is config folder. Okay, let's explain these folders. Here they are. The launch folder will contain the Python launch file necessary to run the model in RViz. On the other hand, the URDF folder will contain the URDF source file of the model. Note again that URDF stands for the Unified Robotics Description Format. This is a file format that's used to specify the geometry of robots and some other properties. And finally, we have this config folder. This folder will be used to store the RViz configuration. Let us now build the complete workspace once more. To build the workspace and packages, we need to navigate to the source folder of the workspace. And again, in this folder, we will type /build. Okay, let's continue. Let's proceed with the step number 4. In step number 4, we need to create URDF and launch source file. First of all, let's navigate to our URDF folder. In this folder, we will create model.urdf file that will contain our URDF description of the robot. To create the URDF file, we'll type this, gedit model.urdf. We will open a new file called model.urdf, and here it is. To make this video tutorial as short as possible, I will simply copy and paste the content of the file, and I will explain this file line by line. But before we actually explain this file, it's very important to understand this graph showing the structure of our system. URDF models robotic systems by using links and using joins. Our system consists of 3 links. We have the base link, we have the first link, and we have the second links. The links are connected by using joins. Here's joint 1 and here's joint 2. Joint 1 is revolute and joint 2 is prismatic. Revolute means that joint 1 can rotate, and prismatic means that the joint can translate. Base link is a cylinder, first link is also a cylinder, and the second link is a box. Over here you can see the dimensions of the links. Let's explain C1, C2, C3, C4, and C5. C1 is the global fixed coordinate system origin at 0, 0, 0. In robotics terminology, this is the world coordinate system or the world frame. At the same time, the base link is centered at C1. On the other hand, C2 is the coordinate system origin of joint 1. Then, C3 is the center of the first link. That is, the center of the first link is placed over here. On the other hand, C4 is the coordinate system origin of joint 2, and C5 second link is centered here. Over here you can see the displacements of one coordinate system with respect to another one. Now that we understand the geometry of our robot, we can go back to the XML file. This first line means that this is the XML file, and over here we specify the version. This is how we write comments. We start the comments like this and we end the comments like this. The URDF file starts with this tag robot, and if you scroll down to the line 60, that is to the end of the file, you will see that this tag is closed. That is, over here we open the tag or we open the environment and we close the robot environment. This is very important to understand. Over here we define the base link. Here is the base link, and let's look into the geometry. Here is the base link. Okay. we start the link environment and we close the link environment. Over here we define the visual description of our link. We define the geometry. It's a cylinder, length of 0.1 and the radius of 0.3. Let's go back to our diagram. Radius 0.3 and the length of 0.1. Length and the radius. And that's the geometry tag. Over here we define the displacement and rotation of the center of our link with respect to its joint. There is no joint. This means that we are centering everything at 0, 0, 0 for RPY. RPY is roll, pitch, and yaw. This means that there is no rotation of this coordinate system with respect to the world coordinate system, and there is no translation. Again, RPY is the rotation in roll, pitch, and yaw, and over here is the translation with respect to the joint coordinate system. Over here we define the material color. I specify the RGBA code for blue. Here it is. We close the visual description and we close the link, and that's it. Next, we need to define joint 1. It's a revolute joint. Let's see how we define this joint in URDF. Okay, we start the joint environment and we end the joint environment. We specify the name, joint 1, and the type, revolute. Now, we need to specify the parent and the child link of our joint. So what is the parent and the child link? Let's see the graph. Every joint needs to have a parent link and needs to have the child link. In this case, the parent link is the base link and the child link is the first link. And that's precisely what's written over here, parent link and the child link. Next, we need to define the coordinate system origin of joint 1. Let's look at the graph. Here it is. C1 is the world coordinate system. We can see that C2 is displaced for 0.05 in the z direction with respect to C1. There is translation. However, there is no rotation. Since there is no rotation, RPY, that is roll, pitch, and yaw, is 0, 0, 0, and over here we specify the translation. 0 in the x, 0 in the y, and in the z direction we have 0.05. Why is here 0.05? Well, if you go back to the cylinder description, you can see that the cylinder length is 0.1. Since 0.1 divided by 2 is 0.05, that's why we placed here 0.05. Next, we need to define the axis of rotation. Let's see the graph once more. This joint should revolve around the z-axis. The z-axis is actually this vertical axis. Consequently, the rotation axis is 0, 0, 1. Then over here we specify the effort. You can arbitrarily choose this number. Since we are not precisely modeling this robot, we specify the velocity. Again, you can choose any number you wish. And over here we specify lower and upper limits for rotation. These lower and upper limits should be in radians. However, double check that. And at the end, we close the joint environment, that is, we close the joint tag. Next, we need to define the first link. It's a cylinder. Here's the definition. Start link, end link. Name, first link. Visual representation, end of visual representation. Then, geometry, cylinder, length of 0.5, radius of 0.08. Next, we need to define the center of this coordinate system C3. This coordinate system is centered at the center of the cylinder. And this coordinate system is defined with respect to C2. That is, with respect to the origin of the joint. This is very important to understand. What's happening over here? We can see that C3 is displaced with respect to C2 for 0.25 in the Z direction. There are no displacement in the X and Y directions, and there are no rotations. Consequently, over here, origin is defined like this: roll pitch, 0, 0, 0, and here's the translation: 0 in the X, 0 in the Y, and 0.25 in the Z direction. And finally, we define the material. We specify RGBA, code for yellow. We end the material, we end the visual, and we end the link. And that's it. Next, we need to define joint 2. Joint 2 is a prismatic joint. This means that the second link, that is this link at the top, can translate with respect to the first link. Joint 2 is defined over here. Name, type, prismatic. And over here we need to define the parent link and the child link. Obviously the parent link is the first link and the child link is the second link. Consequently, we write this. Next, we need to define the origin of joint 2. Here again, it's very important to understand that the origin of joint 2 should be defined with respect to the origin of joint 1. That is, with respect to the origin of its joint that's a parent joint to that joint in the kinematic chain. In the kinematic chain, joint 2 is actually a child joint of joint 1, and the coordinate system center of joint 2 is defined with respect to C2. We can see that C4 is displaced with respect to C2 for 0.5 in the Z direction, and there are no rotations. Okay, we write it like this: origin, roll pitch, 0, 0, 0, and displacement is 0, 0, and in the Z direction 0.5. That's it. Next, we need to specify the axis of translation. In our case, the second link should translate in the Y direction. And consequently, over here, the axis of translation is 0 for X, 1 for Y, and 0 for Z. And that's it. Over here, we define the effort, we define the velocity, and we define the lower and the upper bounds of movement. I will change this, for example, to be -2 and 2. Then, over here, we need to specify the second link. Here's the second link. It's a box. The box is defined by Z, Y, and X dimensions. Over here, you can only see Y dimension and you can see Z dimension. The X dimension is 0.2. So let's define this link. Here it is, second link. Box, we specify the size X, Y, Z. Then, here we need to specify the origin. Where is the origin, or better to say the center of link 2 or second link? It's located over here. Now again, C5 should be defined with respect to C4, and C4 is the origin of joint 2. We can see the displacement in the Z direction of 0.05, and we don't have rotation. Consequently, over here we have 0, 0, 0, 0, 0, 0.05. We specify the material, we specify the RGBA code for red, and material, and visual, and link, and then robot, and that's it. And here again is our file. Line 28, now I will scroll down, line 54, and the end, and that's it. Simple as that. Save the file and close Gedit. The next step is to add the dependencies. How to do that? First of all, we need to go to this folder. But before we go actually to that folder, let's see that we actually have model.urdf. Here it is, that's good. Let's go to this folder. And in this folder, there is a file called package XML. Here it is. We need to edit that file. There is an error pasting this code. Let me just correct this. Over here, we need to add several lines. We need to add this. Here we are saying that our package actually depends on several packages, that is on joint state publisher GUI, robot state publisher, and RViz. This is very important. Save this file and close the file. The next step is to create the launch file. First, let's go to this folder, and in this folder we will create the launch file. Launch file is actually a Python file that's used to properly configure RViz when we launch our package. Over here, I will simply copy and paste the content of the launch file in order to save the time. Here it is. Now, here I have to make one statement and one warning. Often it can happen that while editing Python files in gedit, the tabs inside of the functions and classes are not properly aligned. You see over here, once we define a function, everything under the function should be aligned with the tab. I noticed that, so my suggestion is not to use gedit to edit Python files. Instead, you can use your favorite editor such as VS Code or in my case Spider. Consequently, I will use Spider to explain this file. I will save this file and I will open it from Spider. I will close gedit. I created a separate video tutorial explaining how to install Spider by using Anaconda. A link to that tutorial is also provided. First, I need to start Anaconda. And then I need to start Anaconda Navigator. Note over here that I opened a new terminal to start Anaconda Navigator. This is very important because if you open Anaconda Navigator from this terminal will be occupied. Consequently, always open it from a new terminal. And I will launch Spider. Here it is. Spider is my favorite editor for editing Python files. I really like it since it reminds me of MATLAB. I will open our file. It's located over here. Again, you can use any other Python editor. And here's the launch file. Perfect. Let's explain this file line by line. Over here, we import the necessary functions, modules, and other objects. We import launch, then from launch.substitutions we import command and launch configuration, we import launch ROS, and we import OS. Here's the function that will generate this object over here, launch description, and this function will return this object. Let's explain this function line by line. Over here, we define our package path. We specify the name of the package, again the name of the package. Over here, we define the path to our URDF model. We join the package path with this string. Model.urdf is in the folder URDF. Over here, we define the path to the RViz configuration file. This file doesn't exist currently, however, we will create it at the end. This file is located over here, and here's the name of the file. There will be no error if you start RViz first time without specifying this exact name. So don't worry about that. Over here, I simply print the URDF model path just to verify everything. I use these two lines to read my URDF file, and it will be stored in robot description. This dictionary over here is used to define the robot description. That is, I take this description, I put it as a value, and the key is over here. Over here, I defined robot state publisher node. I use node constructor. I specify the package name. This is the standard ROS package. This is the executable file. Where is the output? The output should be screen. The parameters is actually this dictionary over here, and the arguments is actually URDF model path defined over here. Let's continue. Then I define the joint state publisher node. Again, I call this constructor node, joint state publisher as a package, executable, name, parameters, here they are, and arguments URDF model path. Then I define over here joint state publisher GUI node. Again, name of the package, executable, name, arguments. And over here, I define additional launch conditions. This string over here is actually a name that's defined over here. I will explain this line later on. And finally, I define my RViz node. Package is RViz2, executable is RViz2, name RViz2, output should be on the screen, and over here I specify the path to my RViz configuration file. Over here I extracted the path, and I simply define a list over here that specifies the arguments. This means that RViz will search for the configuration file and will look for this path. Again, we can run first time RViz without this file existing. Later on we will create that file. And over here, what do? We simply create launch description, and here's the constructor. Declare launch arguments, name GUI. Basically, we couple this part with this part, and we set the default value to true. And here is a simple description. This means that we will, by default, start GUI for the joint state publisher. That is, we will have a small window over here in the corner that will enable us to move the joints manually. You will see that later on. And we specify all the nodes that should be started together with our package, robot state publisher node, defined over here, joint state publisher node, defined over here, joint state publisher GUI node defined over here, and RViz node defined over here. And that's it. Simple as that. Again, here's the file. Starts from here, line 34, and ends over here. That's it. You can safely close Anaconda. And we can close also Spider. Since we don't need Spider anymore, there are two ways to do that. You can simply go to the terminal and you can close this window. Okay, let's continue. Final step. Build and run RViz. First of all, we need to edit cmakelist.txt file. And note over here that I'm in the original terminal. And if you scroll all the way up, you will see that we sourced the environment over here. This is very important. Let's go to this folder. In this folder, there is this file. We need to edit this file. Here you can use gedit to edit these files where you don't need basically tabs. Although here you might need the tab. However, it will not create any difference. Above this line, build testing, you need to add this. Install. And over here, you need to specify the folders in which we created source files. They are launch, URDF, and config. This is very important since if you don't specify this while building the package, build will not know where the source files. Here, we tell explicitly the source files are in launch, URDF, and config. And save this file and close it. Okay, let's continue. Now, let's go back to our workspace folder and let's perform the final build of our package. And let's hope that we will not see any error. Let's see. Here it is. Over here you can simply ignore this warning and this error since it always happens. It will not change anything. Next, after you create a package, you actually need to source the setup file of the package. In our case, the source file is over here, and you need to source this. Again, at the beginning of this tutorial, we sourced the environment. Now, we are actually sourcing the setup file of our package. This is very important. And finally, we are ready to launch RViz. We launch RViz like this. ROS2 launch, URDF humble test, that's our package, and the name of the launch file is display.launch.py. So let's see what will happen. Okay, here's our RViz. Let's expand RViz. Where is our model? Interesting. We don't see our model. To display the model, you need to make a few adjustments over here. We will do these adjustments only once, and then later on, we will save the configuration in a separate file such that next time we open RViz, RViz will be properly configured. So let's do that. The first step is to click over here and to find robot model. Click on OK. Expand robot model. Over here, you can see description topic. Click over here and find robot description. If you press enter, you will actually see all the links of the robot placed on top of each other. Okay, that's a first good sign. The next step is to define the fixed frame. So where is our fixed frame? Expand this and select base link. Once you do that, voila, here's our model. Perfect. Let's try to move the model. Now you will notice over here, joint state publisher. That's the node used to manually move our joints. So let's move the first joint. Perfect. We can rotate around joint 1. And you can also see the limits. Let's move joint 2. Here it is. Perfect. We can move joint 2. Let's see the coordinate systems. How to see the coordinate systems? Well, click on Add. Over here, find TF. And let's, for a second, click over here. By doing this, I kind of hide my robot and I can only see the coordinate systems. So what are the coordinate systems? Here's the world coordinate system. That is the base link, the center of the base link. This is the coordinate system of joint 1 and this is the coordinate system of joint 2. Now if you move joint 1, you can see how the things are being rotated. This is the first rotation, and then you have translation. Perfect. Let's save this RViz configuration such that we don't need to adjust this configuration every time we open RViz. To do that, click on File, or better just click over here to make everything enabled. Then click on File, click on Save Config As, and you can see that RViz is already smart enough to go to the config folder. However, let's say that you don't know how to find the config folder. To do that, you need to go to Home, then you need to go to the workspace, you need to go to the source, then you need to click here, and here's the config folder. The name of the file should be config.rviz. How do I know that? Well, if I open gedit again, you can see this path, config.rviz. Consequently, the file name should be config.rviz. So save it like this. Okay, perfect. Now, close RViz. You can also, again, save. It will always ask you. Go back to the original terminal, press Ctrl+C, and then let's build everything again. Go back to the Colcon build. Then, after that, source, and again, start RViz. And you should see your model. Here it is. Perfect. Okay, this is the end of the lesson. In the next lesson, we will explain how to more elegantly define the model and how to parameterize the model by using Zacro programming language.